Okay, for this last section, this is all just review, but it is using stuff that has exponents that are fractions. So if you think about what this means right here on number 38, it just means to add the two problems together. I don't really like seeing it like that, so I'm just going to sort of substitute it. F plus G. So my F is x to the 2/3. My G is 2x to the 2/3. So when I add these things, they have radicals in them. They're cube roots because of the bottom number. But that doesn't matter because all we need to do is add the numbers in front. These are like terms. So this is 3x to the 2/3 because we don't mess with, oh, I forgot a part. It's got the -3 also. So we don't mess with the exponents because they're already like terms. The second one, it's the same exact problem, except this is x to the 2/3 minus 2x to the 2/3 minus 3. So on this one, you have to distribute the minus. So it's minus 2x to the 2/3 plus 3, and then x to the 2/3. This is 1x to the 2/3 minus 2x to the 2/3, so it's negative 1x to the 2/3. And then I have plus 3. That's my answer. The next couple, so we've got multiply, we've got divide. I'll do the multiply first. So the multiply says to take f of x and multiply it to g of x, or h of x actually. So f of x is x to the 2/3, and they want us to multiply it with h of x. H of x is x to the 1/2. So what ends up happening here is these are the exponent rules that we learned in the previous chapter. When you guys multiply things that have the same bases, all you have to do is add the two exponents. So it gives me a single x, and in the calculator, if you go 2/3 plus 1/2, that one actually gives you 7/6. So that would be our answer. In number 41 is a division problem. So if we have a division problem, let's see, g of x. So we've got 2x to the 3rd minus 3. And then we have h of x. H of x is x to the, actually I messed that up. It's not, it's got a 2/3 right here, sorry. And I have x to the 1/2. When we do division, we don't actually really divide them. We just kind of leave them there. That's the answer. H of x times h of x. So I have x to the 1/2 times x to the 1/2. So we just add the two exponents and we get x to the 1. 1/2 plus 1/2 is 1. So you could just put x even. So these questions also will ask us about the domain. Anytime you have a cube root, so it's pretty much based on the bottom number right here. If you have a cube root, the domain is all real numbers. So that's from -infinity to infinity. That just means the graph goes left forever and right forever. If you look at, let's see what we got here. If you look at number 39, this is another cube root. So again, the domain is -infinity to infinity. So the issue is, are there any numbers that won't work? And when you're working with cube roots, they all work. You can have positives and negatives in there. Now, once you get into something that has an even number on the bottom, that's where you have to be careful because now negatives don't work. 0 still works, but negatives don't. So we go from 0 to positive infinity, including the 0. So I have to use a bracket on it. Number 42 is just x. It's a line. Goes left to right forever. So that domain is -infinity to infinity. And then the last one. So the only time we have issues, so first let me talk about the first part. This has a 3 at the bottom, so that doesn't cause any issues. Usually that's -infinity to infinity. But the one at the bottom does cause an issue. Because number 1, we can't have zeros at the bottom. And number 2, because that's even, that means that's the index. So we can't have any negatives in there either. So we have to have any number bigger than 0, not including 0. So your domain for this one would be from 0 to infinity. And we can't put a bracket on the 0 because 0 wouldn't work on the bottom there. You would get an undefined message if you typed it in the calculator. So again, guys, if you don't know domain and range, if you have to guess, I would guess -infinity to infinity. You can see how many times it actually comes up. So that's just if you don't understand what you're doing when it comes to domain and range.